Hello, and welcome to today's webinar on concept-based curriculum, brought to you by MindFuel. My name is Danielle.
And I'm Karen.
We are MindFuel teachers, and we are thrilled that you have decided to join us on this journey.
You've probably heard that curriculum design is shifting, whether it's in state or provincial documents or the NGSS. Teachers are interested in how to make learning less about information overload and more about being an active process that is relevant and engaging for students.
We are seeing the focus of curriculum design shifting from narrow knowledge-based outcomes to an expectation that students, through critical thinking, inquiry, and problem solving, will make connections to concepts, generalizations, and big ideas that are critical in the discipline they are studying. They will look for patterns and connecting ideas that lead to deep learning and that can be applied across disciplines, situations, and time.
So what does this mean for teaching and learning? How will teachers design instruction and assessment to engage student curiosity and develop critical mindedness that connects facts, ideas, and generalizations?
These are important questions, and there is no magic formula. So let's start with understanding what a concept-based curriculum actually is.
A concept-based curriculum is not a program or a strategy. As with any curriculum or program of studies, it identifies what students need to know and be able to do, and the ultimate goal is for teachers and students to apply these facts and skills to understand the big ideas or enduring understandings that are important to understanding the discipline.
In doing so, students will experience learning that is connected, interdisciplinary, relevant, and promotes 21st century competencies.
Viewing curriculum through a concept-based lens means that teachers will be less concerned about whether or not students can regurgitate facts and choose correct formulas. Instead, teachers will emphasize the ways in which students use those understandings and skills in order to develop generalizations about a topic that can be used in novel situations. It should be noted that the facts and processes are still of critical importance. Students must still learn the facts and show competence in the skills. In addition, however, students will be learning how to use those facts and skills to form generalizations that will support their continued and lifelong learning.
Big ideas like the atomic molecular theory of matter or Newtonian laws of force and motion are conceptual understandings. How to apply those concepts in different situations is procedural understanding. Both go beyond facts and skills.
These conceptual and procedural structures will be useful to students because by definition, they must do three things. First, they must cut across time, meaning that the concept can continually be built upon over time. New examples will solidify the concept.
They must also cut across cultures. That means the concept is experienced by all people. For example, Newtonian laws of force and motion are experienced universally, even without knowing anything about the laws.
And finally, these structures must cut across situations. Regardless of the situation, the atomic theory of matter will still apply.
Concept-based curriculum is designed to create student experiences that allow them to draw on knowledge and skills from every subject and facet of their lives so that they can analyze, interpret, seek solutions, and make informed decisions. Few problems they will ever encounter will be solved using just one set of knowledge or skills. Concept-based curriculum recognizes this complexity and responds to it.
Let's compare traditional curriculum design and concept-based curriculum design so we can make sense of the similarities and differences between the two. In a traditional or 2D model, the focus is on developing skills, processes, and knowledge within a specific topic, like cells, for example. Some knowledge and skill components are unique to this topic. For example, learning the difference between animal and plant cells, or how to make a wet mount slide. These may or may not be transferable to other situations.
In contrast, in a 3D model, notice that skills, processes, and factual knowledge are still very important. However, another dimension has been added in which teachers and students must go beyond the basic learning outcomes and consider how the knowledge and skills that they are learning contribute to the bigger understandings about how the world works. Uncovering patterns and looking for generalizations that apply in other situations rounds out the 3D view of curriculum design. In this case, we may consider how the structure and function of cells is a determining factor in understanding the functioning of cell systems, such as circulation and respiration. And understanding cell systems may help us to make generalizations about other non-living systems as well. This kind of understanding is what biomechanical engineers draw upon to create technological supports for human life.
Many skills also cut across disciplines. For example, asking questions, engaging in inquiry, analyzing information, problem solving, critical and creative thinking, and collaborative teamwork. All of these skills are equally important in social studies as they are in STEM disciplines.
To emphasize the differences a bit further, 2D curricula are coverage-centered. This means the content is an inch deep and a mile wide. All that teachers can be expected to do is cover the materials and move on, leaving students with surface knowledge. Students do not have an opportunity to get in on the secrets of thinking like a scientist, mathematician, engineer, historian, or poet. It is no wonder that students leave each class thinking that there's a silo of information to be learned for the test and quickly emptied from their minds to make room for the next information dump.
2D curricula are also intellectually shallow. Students do not need to work hard to process information. They are expected to recreate the skill or information to fulfill the learning outcomes. We'd like students to do some heavy lifting to make sense of the information and apply it, not just know it.
And finally, the 2D curricula is lacking the ability to transfer knowledge to other situations. The material learned is somehow locked in time or space and appears to be limited to the specific topic. There is no opportunity to make generalizations to other situations or disciplines. Today's issues and problems are multifaceted and rarely require just one set of knowledge or skills. Our world is messy. For example, it is not possible to think of global climate without considering biological systems, chemical and physical properties of matter, economics, earth sciences, cultural impacts, etc. Beyond that, it is necessary to consider how each of these disciplines test and analyzes information, including the peer review process, in order to distinguish supported data from opinion. Messy.
In contrast, the 3D curriculum is idea-centered. Facts and skills are still very important because they provide a strong foundation to understand conceptual, transferable ideas, not because of the facts and skills in isolation.
3D curriculum is also intellectually deep. It requires mental processing on a conceptual level, resulting in deeper understandings. Teachers and students need to work at finding connections and generalizations that stem from the facts and skills and make sense of what they are finding.
In 3D curriculum, concepts and generalizations transfer. As teachers and students find connections and patterns, they are able to transfer their understandings to issues and problems in other disciplines and across disciplines, making them better able to understand and deal with complex problems and issues like global climate.
And lastly, 3D curriculum develops intellect to handle an increasingly complex world. We live in a complex world. It can be volatile, uncertain, chaotic, and ambiguous, and that is what makes it both intriguing and challenging. But it requires deep thinking to solve problems, and a concept-based curriculum can aid in developing the knowledge and skills required.
The essence of concept-based curriculum for teaching and learning can be summarized by 2 words: uncover and transfer.
Concept-based curriculum also supports authentic learning using real-world applications. Applying knowledge and skills to novel situations means that students must be confronted with problems and issues that are not easily solvable. They are wicked problems. They may not have one solution. However, the only way to tackle the problem or issue is to draw upon knowledge and skills that have been accumulated across topics, disciplines, and time. This is hard, challenging work, the kind that results in increased confidence, resilience, and satisfaction. The kind that values creative and innovative ways of looking at a problem. The kind that rewards persistence and grit.
The kind that will force us as teachers to reconsider the way we teach and assess.
Concept-based curriculum is supported by backward design as described by Wiggins and McTighe in their book, Understanding by Design. As you may be aware, their approach is to focus on helping students uncover an understanding of important core ideas called enduring understandings and essential skills, and to transfer their learning to new situations. If you have been working with backward design already, concept-based curriculum will make sense to you.
The backward design approach rests on students uncovering the big ideas of a topic of study. They consider big ideas to be those concepts, principles, theories, and processes that are the focal points or essence of a topic in the way that an expert in the area would view it. Big ideas bind together discrete pieces of knowledge and skills within a larger intellectual frame. As students, with teacher support, begin to experience learning within a context larger than an individual topic or unit, they develop the capacities to explain, interpret, apply, shift perspective, empathize, and self-assess, all of which serve as indicators of deep understanding. These are the competencies that teachers will then look for when assessing students.
So what might teaching and learning look like? Let's consider a topic that shows up in every grade to some extent: ecosystems, a complex and messy topic. How might we connect the topics across grades and within subjects to identify big ideas that will allow us to discuss the complexity of ecosystems?
Let's start with a close-to-home local environment, the schoolyard. Ask students what impact humans have had on this environment. Take a walk through the schoolyard and record observations of human impact on a familiar ecosystem. Back in the classroom, collect student observations and record them. Then, discuss possible ways to categorize the observations. What interpretations can we make about human impact on the environment? Is there more information we need to know? Is there any data collection that would help us? Are there people to talk to who will give us more information about our schoolyard? What variables may be important?
Now consider another ecosystem, perhaps another one that students have some connection to in the place where you live. This might be a forest, lake, or a mountain ecosystem. It would be great to visit and collect observations, or do some research asking similar questions as you did with the schoolyard. What interpretations can we make about human impact in this ecosystem? Remember, human impacts can be both helpful and harmful, and don't forget that humans are a part of the ecosystem, not external to it.
Now, let's take a look at what we have learned about two ecosystems we know and see if we can apply our learning to an ecosystem we don't know, like the Arctic. How will we apply our knowledge and observational skills to learning about human impact in another ecosystem? Are there other big ideas that we need to understand first? What knowledge and skills do we need to develop?
Now sit back and think about how you will begin to assess student learning within this type of curriculum. Now that's a wicked problem.
So now it would be helpful if we highlighted some common vocabulary and a model to continue this discussion. Let's start with facts, topics, and units that we are familiar with in current curriculum design. In fact, the structure of the curriculum and textbooks usually divides the topics or units into separate components, indicating to students that each section stands on its own. There is no expectation that there will be carryover or connection between the topics or units. The units are taught separately, experienced separately, and assessed separately. Each one is a silo of information, specific and non-transferable to other topics, disciplines, or situations. This is not a criticism of current curricula or textbooks. It's simply the current reality.
If individual facts, topics, and units are somehow connected through commonalities across them, we may be able to identify some bigger ideas or concepts. Concepts categorize and summarize the facts and topics into larger, more abstract collections that can be transferred to other topics, disciplines, or situations. Dimension 2 of the NGSS in the United States identifies these cross-cutting concepts as patterns, cause and effect, scale, proportion, and quantity, systems and system models, energy and matter, structure and function, and stability and change. Each of these concepts represents something larger than facts or topics, and each concept could be applied to a set of facts or topics.
Generalizations combine concepts to create relationships that are transferable to novel situations and topics. For example, a generalization for our last example might be organisms within an ecosystem form interdependent relationships. In order to come to this generalization, students would need to apply the knowledge and skills they've accumulated about different ecosystems and link the facts to a systems concept and eventually create a generalization that shows they understand the interrelationships among all the biotic and abiotic components of any ecosystem.
Learning is deeper and more integrated. Deep understandings are created versus coverage. Students see that understanding a forest ecosystem can be applied to understanding any other ecosystem. We just need to understand the big ideas. So now, if we learn about wetlands in grade 5 and forests in grade 6, there's a big idea to connect our understandings.
Let's look at another curricular example. This is a list of the topics that students in Alberta currently study in 8th grade science. The learning outcomes are specific to each topic and are organized as knowledge, skills, and attitudes.
But look closely at the titles of the topics. With the exception of one, the remaining 4 use the word systems. Each of these topics examine different kinds of systems. The structure of the curriculum begs to be looked at with a conceptual lens connected by the questions: are there commonalities or patterns within each topic that would allow us to come up with a generalization about the concept of systems? Structuring teaching and learning around big ideas is not necessarily new, but it is more intentional in the architecture of a concept-based curriculum.
Systems is a big idea. It cuts across biological, chemical, mechanical, and environmental sciences, to name a few. Systems even cuts across other disciplines, such as the ideological or belief systems in social studies, or number systems in mathematics.
The conceptual understanding of systems is complex and interdisciplinary concept and is larger than facts and skills. It is not constricted by time, place, or situation. Systems tie multiple facts, ideas, and processes together.
What is common among the different topics in the list from grade 8 that can be captured under the big idea of systems? We can try to link the units together by connecting concepts.
For example, what if we could create a concept map for each topic linking knowledge and skills, and then enlarge the concept map by adding the next topic and the next? Like a spider's web, making connections where we didn't realize any existed. That might take up an entire bulletin board or a wall by the time we're done. But think of the intellectual exercise that students and teachers would go through. Learning would be more than a string of factoids. It would be complex and sticky, just like the spider's web.
Begin thinking about topics in your curriculum. And in the meantime, we'll give you examples with these topics now.
Let's consider a backward design model for our 8th grade science program.
Each unit is made up of knowledge, skills, and attitude outcomes. For the most part, these outcomes represent what students need to know and be able to do, 2-dimensional.
Now add the 3rd dimension. What's the big idea? We've identified systems as a connecting big idea between at least 4 of the 5 units. If we want students to add that 3rd dimension, they need to look for ways in which the facts and skills they are developing in each unit are building a set of commonalities or patterns.
Would it be possible to connect the unit entitled Mix and Flow of Matter? It doesn't specifically identify systems in the curricular topic, but certainly there are physical and chemical systems that might be connected.
Here are 2 examples of facts. Describe the movement of gases and liquids in and out of cells during diffusion and osmosis based on concentration differences. And explain how objects are seen by the eye and compare eyes with cameras.
In our 8th grade example, as students learn and investigate the facts, they are also asking how these pieces of knowledge help them to construct a system. In one place, the curriculum asks students to apply the concept of a system in describing familiar organisms and analyzing their general structure and function.
In order to do this, they will have to define for themselves, refined by the teacher, the concept of system. Can they apply the definition to both topics?
And what about skills? As students experiment and experience each topic, let's discuss the big ideas of correlation and causation as they relate to our findings. In science, economics, medicine, and many other areas, more faith is put in correlation rather than causation. Why?
How's that concept map coming along? Students are doing some heavy intellectual work here, aren't they?
Now it's your turn. Look at the set of facts, skills, and topics that you're currently teaching. Then ask, what is the concept or concepts that could tie the topics together? What big ideas are important for students to take away? And finally, what generalizations do you want your students to make?
Now, consider possible student preconceptions, possible inaccurate generalizations that students may have come up with. Also, consider how you might use inquiry, blended learning, interdisciplinary connections, etc. Are there real-world issues or problems that can be introduced?
We want to continue this journey with you. What support are you hoping for as you prepare for a concept-based curriculum now and in the future?
Please share your ideas in the comment section below so that we can begin to build a professional and collaborative dialogue. If you would like to see more webinars on this or other topics, please let us know.
Thank you for joining us today. We hope we got you thinking about using a concept-based approach to teaching and learning in a STEM classroom.
Until next time, I'm Danielle.
And I'm Karen.
And we're your MindFuel teachers.